Welcome to Control 4 Driver Development Essentials. My name is Peter Casenza. In this video, we'll examine the ways that a device driver facilitates communication within the Control 4 system. We'll look at each of the supported communication methods and expose the parts of a driver that support the communication needs for a device. To accomplish this, we'll discuss several APIs delivered in the DriverWorks SDK, and using the driver editor environment, we'll see how those APIs are used. As we discussed in the Evaluating a Device for Driver Development video, Control 4 supports IR, serial, and IP communication methods. If you are unfamiliar with those methodologies, or have not yet had a chance to watch the device evaluation video, now is a good time to do that. Let's start with IR communication. IR drivers represent a large number of device drivers in the Control 4 driver database. They're a popular choice for controlling devices that don't necessarily require two-way communication to achieve a desirable level of control. Devices such as satellite receivers are good examples. If you need to develop a simple IR driver, say for example to control just a TV, you may want to consider using the Driver Wizard suite found in Composer Pro. This offers a fairly easy way to create a simple IR driver. However, if your device driver is more complex and perhaps uses several communication methods within it, the DriverWorks SDK and Driver Editor represent powerful sets of tools to the driver developer. Now, let's break down the communication steps involved in sending an IR command from a remote to, say, change a TV channel on a satellite receiver. From the user perspective, the act of changing a channel seems insignificant. The remote is picked up and the channel up button is pushed. Pretty straightforward. However, quite a bit happens from a device driver and device control standpoint. So how does this model apply to a controlled environment where we're not using the provided TV remote and our TV and satellite receiver need to reside in a Control 4 system? Well, our device drivers contain the IR codes needed to control the TV and the satellite receiver. When a user picks up a Control 4 remote and presses channel up, it executes the appropriate IR codes associated with channel up from within the drivers. Let's take a look at this in the Driver Editor environment. We'll use a DirecTV satellite receiver as an example. This particular receiver is model HR10-250. If we load this driver in the Driver Editor environment and click on the Codes Command sections, we'll see all of the IR codes that the device supports. About halfway down is our channel up command. If we double-click on the command, it opens up the code editing window. This gives a good look at the numeric string that make up the IR code. There are some interesting configuration points in the code editing window as well. Along with the actual code content, we can configure this code to repeat itself however many times we feel is needed. Along with that, we can configure how long to wait between sending the code. This value is in milliseconds, by the way. You'll also notice a transmit field. Its value is always pulse. We can also see the name of the IR code and the Control 4 proxy to which this particular code is associated. Before we get ahead of ourselves, it's important to keep in mind that we've been looking at an existing IR driver. Your job as a driver developer will be to obtain these IR codes for the device your driver will control. With this in mind, you'll notice the ID field in the upper left-hand corner. This ID value lets you assign a unique value to an IR code. Remember this field, as it will be very useful to your driver development efforts, and we'll come back to it in a few minutes. As I mentioned, you're going to need to include the IR codes for your device in your driver. The right-hand side of the code editing window will help you with that. The IR Code Capture tab is a great way to passively capture codes from a remote. You simply connect to a Control4 controller and record the IR codes based on button presses. Once captured, you can edit the code if needed, configure its performance, and assign it an ID. You can also copy and paste an existing IR code into the primary IR code area section and save it. You can also generate codes in the IR code entry tab. Driver Editor provides the most popular IR code formats such as Sony, NEC16, and RC5. If you know the associated code information, such as customer code, system, and command, Driver Editor will generate an appropriate IR code for you. Now that we've taken a look at IR codes and how you can interact with them through Driver Editor, let's look at some driver code that uses them. Remember our channel up command? Well, here it is in our driver. Its ID is 104, as we saw in the code editing screen in Driver Editor. It's there along with all of the other codes the driver will use. These are found in the IR section, IR codes area of the satellite receiver driver. So, when the channel up button is pressed on the Control4 remote, it sends the channel up code, which is ID 104, to Director. Director then sends the code out of the port on the controller to the device, which then increments the channel. This code is sent using the sendIR API command. Let's take a look at the API documentation to learn more about IR API functions that are important to driver development. Here is our sendIR API documentation. Based on the information here, we know that in order to use the API, we need to send the control connection ID value for the device we're controlling, as well as the ID for the IR command we wish to send. While IR codes can be complex, the manner in which they are handled within a driver is rather simple. An IR code is sent to Director using the sendIR command. Director then responds by executing the code and controlling our device. Your IR driver's job is to send the correct command using the appropriate settings to achieve device control. Let's take a look at another means of device communication supported by Control4, serial, also known as RS-232. Serial control offers driver developers a feature that IR does not. It supports two-way communication. When we refer to two-way communication, we are talking about the ability to send commands to a device and receive status and feedback from that device. This is not insignificant, especially when you consider the benefits of being able to ascertain a device's state before you send it a command. Before we look at any driver code, let's take a brief look at the serial communication protocol to get a better understanding of how it works. When you look at a serial plug, you'll notice the pins inside the plug itself. Each of the pins has its own job when it comes to sending and receiving data. For example, on the standard 9-pin RS-232 connector, pin 3 is designated to transmit data, pin 2 is tasked with the job of receiving data, and pin 5 is the common ground. When you create a driver based on serial control, the Electronic Industries Association RS-232 standard is assumed. Now let's go back into Driver Editor and take a look at some of the properties of serial communication that you'll want to consider when creating a driver. The driver we're currently reviewing is a Sony STR series receiver. This driver was created using the DriverWorks SDK. If you open the driver and click on the Configuration tab, we can see the serial port settings. You'll want to obtain this information for the device you're working with. The settings include baud rate, data bit, parity, stop bit, and flow control. Let's take a moment and discuss each of these and how they might impact your device driver. Baud rate refers to the data transmission speed. It is measured in bits per second. This value defines the frequency of each bit period. For example, if a baud rate of 9600 is used, or 96 bps, the frequency is 9600 Hz. This is the information that the Sony receiver uses to recover the bits from the data stream. While some devices can be configured to support multiple baud rates, a Control4 driver can only be set for one. So, it is important to include in the driver documentation which baud rate is supported by your driver. The data bit value refers to how many data bits are transmitted. Our Sony receiver uses an 8-bit transmission, and that's fairly common. You can choose data bit values because ASCII is made up of the alphabet within the first 7 bits. This includes control characters. The 8th bit extends the character set for graphical symbols. If you need to transmit raw binary data with your driver, you'll need 8 data bits. Parity is a value that is unique to a device. It provides a form of error detection when you're transmitting data. Valid values are odd, even, or no parity bit, in which no parity bit will be transmitted. You will need to ascertain the correct parity value for your device. Stop bit simply provides a period of time before the next set of data bits can be transmitted. Stop bit options include 0, 1, or 2-bit periods. Now that we have looked at the serial connection properties, let's go into the Sony receiver driver and see how they are implemented. If we take a look at the properties section of the driver, we'll see all of the settings that we have just discussed. This is also a good time to look at some serial control APIs that are available through the DriverWorks API reference guide. Remember when we mentioned that serial control has a significant benefit as it provides the ability to receive feedback from a device. This feedback comes through on an API called Received from Serial. This API requires the control connection ID through which the data was received, along with the actual transmitted data from the device. Send to Serial is another API worth mentioning. It provides a means to send data to your device. Like Receive from Serial, it requires a binding ID and a data string. Using these two APIs, we can send commands to our receiver from a remote or a touch panel, and then receive information back that indicates status or provides us with the ability to enact further control measures. The last type of device communication I'd like to discuss is Transmission Control Protocol Internet Protocol, also known as TCP/IP. The first half, or the TCP half, is used for transmitting data from an application to the network. It is responsible for breaking down data into IP packets before they are sent and for assembling packets when they arrive. The second half, or the IP half, takes care of the communication with all of the devices on the network. It is responsible for sending and receiving the data packets over the internet. Like serial communication, TCP/IP also provides two-way communication. Let's go back into Driver Editor and look at an example of a TCP/IP driver. In this example, we'll open up an AV switch that is controlled over a TCP/IP connection. When I click on the Connections tab and scroll down to the TCP/IP Connections icon, the Edit Connection screen is displayed. Here, we can see that Network has been entered as the connection type. The driver developer has assigned a connection ID value of 6001 for the driver. This control connection ID is useful as it is an internal identifier that is used to uniquely identify the connection. This connection ID will be passed in APIs and looked for by applications that need to consume data from your driver. The connection name given is TCP/IP connection. This value will be displayed in several areas throughout the system, so correct identification here is useful. The connection class is set to TCP. This value is important as the Control4 operating system will use this value to designate your driver as using TCP/IP. It is required to assign a port on which to transmit your data. There is an established set of available ports for various types of data transmission. In our example, the driver developer has chosen port 23. This port is used for transmitting unencrypted data. Now, let's go into the driver and see where these settings are used. If I open the AV switch driver and go to the connection area, we'll find all of the settings we saw in Driver Editor. In this section, you'll define the properties of your TCP/IP connection. Here, we see the connection ID, the connection name, and connection class information. Just like IR and Serial, TCP/IP uses several APIs to send and receive data. The first API I'd like to mention is Send to Network. Send to Network allows us to send requests or commands to the network and ultimately to our device. It requires the binding ID we discussed in Driver Editor, the port, and finally the data packet itself. The other important API we should discuss is Received from Network. This API allows us to receive data packets from the network to ascertain device status. It requires the same parameters as Send to Network, a binding ID, a port, and the data. There are certainly more nuances behind each of the communication methods we've talked about in this video. However, the information offered here should get you started on not only understanding the basics of each method, but also gain an understanding how each are used within a driver.